All right, here we are talking about rate graphs. Let me make myself small. Okay, so a rate graph is something that we're going to see in calculus a lot because, this is where they use a lot of calculus, right? Because they use it to define how much something is changing over time, and then they, evaluate that. Okay, so basically, if you think about the rate graph, so for this one, we have a rate. The horizontal axis is in terms of time, and then the vertical axis is in terms of a rate of rainfall. So it tells us what the rate of the rainfall is at that um, exact moment. And so before we've been seeing like position functions and velocity and acceleration. And what you can think of, the rate graphs kind of fall right here in the velocity graphs category, right? So we've got position as the original function, then velocity as the derivative, and then acceleration is the second derivative. And a rate graph falls in the same category as velocity. It's a first derivative, right? Because a rate is the slope of an original function, right? Any rate is the slope. Okay, so when you see a rate graph, you're looking at the graph of a derivative. Okay, we're looking at a derivative, so we're looking at the second tier on the totem pole. So you can think about a point on the graph. It represents a rate at a certain time. So like for this one, if we said when time equals 3, f of 3 is 1, which means when time equals 3, the rainfall is falling, the rate of rainfall is 1 inch per hour. And this is really important. We had a question on the last test that dealt with deer population, and a lot of people forgot that the rate of change, we need to have some units on it. So think about this, the time, like something per something, right? So inches per hour is what a rate would be. And then the slope of this graph is going to represent the rate of change of the rate. So how fast is the rate of change changing? So remember that like a rate is indicated as something per something, right? Well, then a second one, if we think of like acceleration, it would be something per hour, right? Like inches per hour, miles per hour. Then when we're talking about things like acceleration, that's the unit we use is like miles per hour. That's how fast they're accelerating. And then the signed area between the graph and the horizontal line represents a definite integral which has undone the indicated rate and produced an accumulated value. So the important part here to think of is all of this shaded area under the graph. This basically tells us how much accumulates over time of some function. And this is where calculus is useful because people use this for things like, weather, but also for business when they're looking at accumulation and rates of change of markets and things like that. So if you think about it, the integral basically is an accumulation function. It's showing us how much has accumulated over time. Okay, so the graph at the right models rainfall from midnight to 6 a.m. So time equals 0 is midnight, and time equals 6 is 6 a.m. And this is where, we talked about how sometimes you can have 0 time. This is, or negative time. This would be something that you could look at if they had a graph that kept going, if it went back. Time equals -1 could be 11 p.m. of the day before or something like that. But anyway, so write a complete sentence to explain what point A on the graph means. So remember, this is a rate graph. So think about this as the derivative, right? This shows the rate of change of the rainfall. How fast is the rain falling? And so write a complete sentence about what point A represents. And include numbers and units in your answer. This is the key that I think that we missed a lot when we were looking at this before, is using numbers and units in the answer. So not just saying like the rate of change at t equals 3 is 1. let's say a little bit more, or the rate of change at that exact point equals 1. Okay, so let's be a little bit more descriptive. So who cares what this graph means? That's what we're trying to figure out. What does it mean? Well, it means that at time equals 3, right? At time equals 3, the rate of the rainfall is 1 inch per hour. If I put in time equals 3 into this graph, I get out 1. Okay? And what does time equals 3 really mean? It means at 3 a.m. it is raining let's see, at a rate of 1 inch per hour. That's where we hiccup a lot, is that a lot of people would say, like, at time equals 3, the rate equals 1. And we don't know what 1 means, and we don't know what time equals 3 means. Is it 3 minutes, 3 hours, 3 seconds? So let's be descriptive and say at 3 a.m. it's raining at a rate of 1 inch per hour. That means at that exact moment it's coming down at 1 inch per hour. What is the slope between points A and B on the graph? Well, if you look at it, there is a slope of 0, right? They don't change. So the slope between A and B is 0. Write a complete sentence to explain the meaning of the slope being 0. And now, does that mean that no rain fell in between A and B, between 3 and 4 a.m.? No, because we're looking at a rate graph. We're looking at rates, right? So the rate at 3 a.m. is 1 inch per hour, and the rate at 4 a.m. is also 1 inch per hour, which really just means that between 3 a.m. and 4 a.m., the rate of change of rainfall stayed constant, or we could say there is no change in the rate of rainfall. Or you could say that it stayed constant. Yeah, let's write that. The rate of change stayed constant at 1 inch per hour. Okay, so what does that mean? It means that just kept raining the exact same speed. It didn't get more or less necessarily, but it just kept raining. And if you think about this, sometimes I think about this as a speedometer because it's just the easiest way for me to think about it. Basically, it means you just stayed the same speed, right? You just stayed the same speed. You didn't speed up. The rain didn't speed up. The rain didn't slow down. It just stayed the same speed. That doesn't mean that the rain didn't keep coming. It kept coming. It just kept coming at the same speed. Okay, so let's look at some other ones with this one. So what is the slope of the graph between points B and C? So let's go ahead and count. So you count over, let's see, rise over run. So we count down, and you might be tempted to count 1, 2, 3, 4, 5. But let's look at our units and realize that from B down here, that's really only 1, right? We just had different units there. So the rise is, it went down 1, and then it went to the right 1. So our slope is -1. Write a complete sentence to explain the meaning of that. All right. So from, let's see, from point B to point C is from 4 a.m. to 5 a.m. And then what happened between 4 a.m. and 5 a.m.? Well, the rate of rainfall, right? The rate of rainfall went from 1 down to 0. So the rate of rainfall was at 1 inch per hour, and then it decreased to 0 inches per hour from 4 a.m. to 5 a.m. So we could say decreased from you know, actually we're going to talk about like how the slope instead of, because yeah. So it decreased. Now decreased means we're talking about what the slope of that line is. So how fast did it decrease? How fast did the rate decrease? Decreased at a rate of -1 inches per hour, right? So that's the derivative. The derivative of this line is -1, which means that this rate decreased at a rate of -1 inches per hour. Okay, so it's basically like an acceleration thing. Deceleration, if you believe that that's a word, which some people don't. But so basically the rate of rainfall decreased. So there was like a deceleration of rainfall. Okay, find the definite integral from 3 to 5. So we're going to look at the actual area in between. I'm trying to keep it all in the spot, but I'm really terrible at writing small. So from 3 to 5 basically is the area under that curve, right? So let's look at this rectangle first. It's a 1 by 1 rectangle, right? So that's 1 times 1. That's the area of that. And then this is a triangle here, and that's a 1 by 1 triangle. So we're going to add a 1 by 1 triangle. And remember, the area of a triangle is 1/2 times base times height. So we're going to end up with 3/2. Write a complete sentence to explain the meaning of our answer. Well, basically, what this means is that this is an accumulation. Remember, the signed area underneath a curve is accumulation. So how much rainfall actually fell in between 3 and 5 a.m.? Well, we would find the area under the curve of the rate function. So how much rainfall actually fell? This tells us that between 3 a.m. and 5 a.m., 1 1/2 inches of rain fell. Okay, and then approximate the value of 0 through 6 using geometric regions and show our computations. Okay, we got a little bit of time, not a lot. Okay, so let's approximate our actual values. And I'll use a color that we can see. So we're going to try to make a geometric region. And honestly, I think the best way to do it is just to draw a triangle here. You know, I am terrible at drawing straight lines with this thing. All right, we miss a little bit. See, we underestimate here and we overestimate here. But those kind of make up for each other because we're just getting an estimate, right? So our very first triangle is a 3 by 1. And then we add that to what we already have, right? So our very first triangle is 3 times 1 over 2, because that's how we find the area of a triangle, and we add that to the 3/2 we already have. So we end up with 3/2 plus 3/2, which is 6/2, which is 3 inches. So we estimate that 3 inches fell during, we estimate that from midnight to 6 a.m., 3 inches of rain fell. So that is what the area under the curve means. It's an accumulation of everything that's happened over time.